Now that we've completed the lecture for the derivatives review, we're going to go over some practice problems. I'm going to divide all of the sections in this course into a general lecture with some quick examples and then some more complicated examples in a separate video. So first example, let's find the second derivative, f double prime of x, if f of x is x to the fifth times sine of 2x plus 3. In these more complicated derivatives that we're going to do, the first question that we need to ask is, are we using the quotient rule, the product rule, or the chain rule? As a whole, are these functions multiplied together, divided, or is it function composition? And although we have some function composition in this function, the 2x plus 3 inside of sine, as a whole, we have two functions multiplied together, this x to the fifth times the sine of 2x plus 3. So first, we're going to use the product rule. So this is to find the first derivative, and then we'll find the second derivative after that. So the product rule says that we are going to take the derivative of the first function times the second function plus the first function times the derivative of the second function. And if we write it out like this, we're going to take it step by step, and now we can ask each of these separate derivatives that we have to do, is it a straightforward derivative, or is it a product, quotient, or chain kind of thing that I need to do? The first derivative here is just straightforward. It's just going to be 5x to the fourth times the sine of 2x plus 3. And then for the second one, we need to use the chain rule. We're going to have that our inside function is the 2x plus 3, and our outside function is the sine of whatever. So to take the derivative of the outside function, we're going to take the derivative of sine, which is going to be cosine of, we're going to leave the inside alone, so cosine of 2x plus 3. And then I'm going to multiply by the derivative of the inside function, which is just going to be the 2. So 2 times cosine of 2x plus 3 is the derivative of sine of 2x plus 3 using the chain rule. And this is our first derivative, f prime. Now we're going to try to find the second derivative of a more complicated function. And we're going to have to do two different things. So to find the second derivative, we're going to find the derivative of this first chunk, 5x to the fourth times sine of 2x plus 3. And then we'll find the derivative of the second chunk, this 2x to the fifth. I'm going to bring the 2 out in front, cosine of 2x plus 3. So two derivatives that we have to do here. Both are going to be pretty similar, and both of them are going to use the product rule. So let's do one at a time. The first one is going to be the derivative of the first function, 5x to the fourth, times the sine of 2x plus 3, plus the 5x to the fourth, times the derivative of sine of 2x plus 3, which we already did previously. So we can skip some steps here. We'll do the second one in a little bit. So the derivative of 5x to the fourth is going to be 20x cubed. Bring the 4 down out in front, multiply by the 5, decrease the power by 1. And we have sine of 2x plus 3 plus 5x to the fourth. And then we found out that the derivative of sine of 2x plus 3 is 2 cosine of 2x plus 3. So there's our first derivative we're going to do. And then the second one, we're also going to use the product rule, just with some different functions. So we're going to add all this together. Next one, we're going to have the derivative of the first function, 2x to the fifth, times the second function, cosine of 2x plus 3, plus the 2x to the fifth, and then times the derivative of cosine 2x plus 3. The derivative of 2x to the fifth is just the power rule. It's going to give us a 10x to the fourth. We have a cosine of 2x plus 3 that comes along for the ride, plus a 2x to the fifth. And then this cosine of 2x plus 3, we are going to use the chain rule here. In a very similar way we did the previous chain rule, we're going to take the derivative of the outside function, cosine, which is going to be a negative sine. We're going to leave the inside alone, 2x plus 3, and multiply by the derivative of the inside, that 2. And there is our answer, a long, complicated derivative. All right, next example. We have find f prime, so just the first derivative this time, if f of x is the square root of x to the fifth plus 7x plus 3 all over 7e to the 3x. Complicated function, but as a whole, we need to answer, is this a product, a quotient, or is this function composition? Is this going to be a chain rule kind of problem? And although there is some chain rule, although there may be some product kind of stuff in there, as a whole, this is a quotient. We have a top function and a bottom function. We are going to use the quotient rule here. So, quotient rule says take the derivative of the top function. So we're going to take the derivative of square root of x to the fifth plus 7x plus 3 times the bottom function, 7e to the 3x, minus the top function, square root of x to the fifth plus 7x plus 3, times the derivative of the bottom function, 7e to the 3x, all over 7e to the 3x squared. And if I write it like this, I can see that I now have 2 more derivatives to do, and each of those are slightly less complicated than the one before. And we have to ask the question, is it product, quotient, or chain for each of those? The square root one is a big chain rule problem. This is going to be the inside function is x to the fifth plus 7x plus 3. And the outside function is the square root of something, or square root of x. When I take the derivative of that, this is going to be x to the 1/2 power. This is going to be 1/2, whatever's on the inside, to the negative 1/2 power. We're going to leave the inside alone. And we're going to multiply by the derivative of the inside. And that's going to give us total this 1/2 x to the 5th plus 7x plus 3 to the negative 1/2 times the derivative of x to the 5th plus 7x plus 3, which is 5x to the 4th plus 7. All of that is going to be multiplied by 7e to the 3x minus square root of x to the 5th plus 7x plus 3. We have the bottom is the same, and we just need to figure out this other derivative here. And this 7e to the 3x, again, is going to be a chain rule problem. Here, the inside function is 3x. The outside function is e to the x, or you could even think about like 7e to the x, or 7e to the something. The derivative of the outside is going to be 7e to the something. We're going to leave the inside alone. And we're going to multiply by the derivative of the inside function. Note that you could have brought the 7 out in front as a constant, but you can include it in your calculations as well. It doesn't really make a difference. And altogether, this is going to be 7e to the 3x times the derivative of 3x, which is 3. The answer to these derivative questions are going to be very gross, but that's because we're doing some complicated derivatives here. All right, one more big derivative problem. We have find ddt of natural log of 1 over t squared cosine of cubed root of t. And again, the question we have to ask ourselves is product quotient chain. Is this two things multiplied together, two things divided, or is it a function within a function? In this case, we have as a whole, this is going to be chain rule. We have our inside function is the 1 over t squared cosine of cubed root of t. And the outside function is natural log of something. So as a whole, we are going to do the derivative of natural log is 1 over t. So we're going to have 1 over the something, the 1 over t squared cosine of cubed root of t, that's the inside function, times the derivative of the inside, 1 over t squared cosine of the cubed root of t. And now I have a new derivative to do, this derivative of the inside. And as a whole, we're going to use the product rule here. So as we go forward, we're going to have this gross thing on the outside. And then times the derivative of the first function times the second function plus the first function times the derivative of the second function. And I'm going to do a little housekeeping here. I am going to write not 1 over t squared, but t to the negative 2. And I'm not going to write cubed root of t. I'm going to write t to the 1/3. Makes it easier to do those derivatives. So everything in black here is just going to keep on coming along for the ride. The derivative of t to the negative 2 is going to be negative 2t to the negative 3 using the power rule. And the derivative of cosine of t to the 1/3, we're going to have to use the chain rule again here. Inside function is t to the 1/3. Outside function is cosine of something. So we're going to take the derivative of the outside function, cosine, that's going to give us a negative sine. We're going to leave the inside alone, t to the 1/3, and we're going to multiply by the derivative of the inside function, which is going to be 1/3 t to the negative 2/3. There's a lot of simplifying we could do there, but we're going to say this is good as is. We're not going to simplify these complicated derivatives unless we need to. So then we're going to look at some other kind of problems we can do with derivatives, some ones that you've seen before in Calculus 1. First of all being the equation of a tangent line. So here we're going to find the equation of the tangent line of a function x times 2 to the x at a point x equals 3. So let's remember that equation of the tangent line here equation of tangent line of f of x at x equals a is y equals f of a plus f prime of a times x minus a. This f prime of a, this derivative, is the slope of the tangent line. So what we need to find here, in this case, our a is 3. It's our x value. And our f of x is x times 2 to the x. So we need to find the function evaluated at 3 and the derivative evaluated at 3. We can plug it in. So f of x is x 2 to the x. And if I plug in 3 to that, I'm going to get f of 3 is just 3 times 2 cubed, 2 times, or it's going to be 8 times 3, which is 24. To find the derivative, I'm going to use the product rule. So that's going to be the derivative of the first times the second plus the first times the derivative of the second, which is going to be a 1 times 2 to the x plus x times natural log of 2 to the x. And if I want to find that evaluated at 3, that's the slope of the tangent line, I'm going to have 2 cubed plus 3 times natural log of 2, 2 cubed, which we'll write as 8 plus 24 natural log of 2. So the equation of the tangent line will be y equals f of a, which is 24, plus this gross number, 8 plus 24 natural log of 2, but it is just a number, times x minus 3. Let's remember quickly what the tangent line is doing. We have some function here. Say we're doing it x equals 3. We're saying this is the line that touches the function at that one point. And the slope of that tangent line is telling us how much that function is changing the derivative at that point. One last example in this section, more of a word problem kind of example. Let's say that for t minutes, t greater than or equal to 0, the temperature H of a pot of soup in degrees Celsius is given by the formula h equals 5 plus 95e to the negative 0.054 t. We're going to answer some questions about what this function's doing. So first one is the temperature increasing or decreasing with time? In order to think about increasing and decreasing, let's remember that increasing is when the derivative is going to be greater than 0. Decreasing is when the derivative is less than 0. So in order to figure out if it's increasing or decreasing, I'm merely going to be finding the derivative and seeing if it is positive or negative. So I'm going to look at the derivative. That is going to be h prime, or the derivative of h with respect to t. It's the same thing as saying dh dt is going to be the derivative of 5, which is 0, plus we're going to have the 95 out in front. And then to do this derivative, I'm going to have to use the chain rule. Inside is negative 0.054 t. Outside is e to the something. And the derivative is going to be this negative 0.054 times e to the negative 0.054 t. That is, the derivative of e to the x is just e to the x. We're going to leave the inside the same, and the derivative of negative 0.054 t is negative 0.054. So rewriting this, this is going to be the negative 0.054 times 95 e to the negative 0.054 t. We may notice that this 95, that's something that's greater than 0. E to anything is going to be something that's positive. That's because e to the t is going to be always above the x-axis, something like this. Something like this is like e to the negative t. This guy is like e to the t. If it's always above the x-axis, always positive. And then this last chunk here, negative, is a negative number. So that means that this whole thing is less than 0. So that means that the temperature is decreasing with time, which makes sense. If we think about a pot of soup in degrees Celsius, as time goes on, it's not going to increase in temperature. It's going to decrease as it's just sitting there. And then we can say, how fast is the temperature changing at t equals 1? Well, that's just going to be plugging in 1 into this function, which will be negative 0.054 times 95 e to the negative 0.054 times 1. Use that calculator to find that, but more importantly, what we want to focus on is what are the units here. So this is a rate. It's going to be degrees Celsius divided by minutes. This tells us how many degrees it's going to change per minute. That's our important thing there, is the units. All right, next we're going to look at antiderivatives, and we'll do a lecture and a practice video with that.